Hello everyone, welcome back from spring break. I'm here with a new video on Recitation 8 on gradually varied flow. We'll be taking a look at three problems on water surface profile and that will be sketching. So before we begin, quick announcements on a couple of things. Since we're moving to remote teaching, there are going to be some room for improvement. Let me know if the audio or video or certain aspect of the recordings are not working or can be improved. Lab 1 is due this week. On course site you should be able to find submission folders to submit this. Make sure you take a look at the instructions for naming your files. The first person on the team list is going to be responsible for the submission of the files. The lab report will have to be in PDF format, and while you convert it to PDF, check if the expressions, symbols, equations appear as they should while you convert it to PDF. As far as schedule goes, we'll stick to our normal schedule, Wednesday, Thursday, and Friday at 1:35 p.m. I'll be there. I'll set up a Zoom meeting at 1:35. That way you can ask any questions you have for the material this week. Quiz will begin at 2 o'clock. It will be a timed quiz. The format is going to be slightly different given it is taken remotely. I'm thinking about breaking it down into smaller pieces. That way what I can't do by giving partial credit will be compensated by breaking it down into smaller sections. So getting to this point, the expectation is that you know what normal depth and critical depths are. When you sketch water surface profile, and let me step back, the most important part in open channel flow is knowing where the water surface will be. So sketching water surface profile is our solution to where the water surface will be for instances where the water surface is changing because of various reasons, and mostly in this case we're concerned about the water surface change due to change in water due to change in channel bed slope. So in this problem, there are a couple of lines. The line with larger dashed line, so this is your normal depth. The line with smaller dashed lines or smaller dashes is your critical depth. So here this one is your normal depth and this one is your critical depth. The other way you can always identify which one is your critical depth is by looking following the line across where the change in slope occurs. So the critical depth line is the same no matter what the slope is for the same discharge and the same channel width or the channel geometry. So here this line for normal depth, as you can see, is different for a steeper slope compared to a more gentler slope. And before we start sketching, it is important that we take a quick look at what all these different surface profile curves are and what they mean. So I've copied table 6.3 from your textbook. On the very right hand side are the curve numbers for mild, critical, steep, horizontal, and adverse channels. So the letter means whether the channel itself is mild, critical, steep, and so on. And the numbers following it represents the region where the water surface is at. Since critical depth and normal depth are important in identifying or classifying this, especially the numbers here, let's take a quick look at this. Region 1 is where the water depth is greater than both your normal and critical depth. Region 2 falls in between your normal and critical depth. Region 3 is the region closest to the channel bottom, and it is less than both your normal and critical depth. And this relationship is true for all the different channel types or the different channels. So for critical channels, the normal depth and critical depth, they overlap. So region 2 disappears, so we don't need to worry about region 2. So you have just region 1 and region 3. For horizontal, the normal depth is mathematically infinity. So for all practical purposes, region 1 doesn't exist. You don't have to worry about it. So what you have are region 2 and 3. Adverse channels also have mathematically a normal depth of infinity. So you have again just region 2 and region 3. And here you'll notice for mild, critical, and steep channels, the slope is greater than 0. So all the channels are sloping downhill. If the channel bottom is horizontal, then it's a horizontal channel. If the channel is going uphill as the water flows, that is going to be an adverse channel. So the letter and the numbers together, they explain the relationships between the normal depth and critical depth to the water level, and also gives you information about the channel slope. Now going back to our first problem, we first want to identify where the control points are. So control points are locations where we know what the water depth is. So in this case, there are two channel slopes, and we know the relationship between the normal and critical depth, so we can classify what the channels are. So in this case, the normal depth is greater than critical depth, so that makes it a mild channel. So for the upstream section, the normal depth is smaller than your critical depth, so that makes it a steep channel. So after you have identified the channels, then you can go ahead and take a look at the control points or control sections. So right at the inlet, in a steep channel, we know the water will be at critical depth. So this is our control point here. The sluice gate also forces water to be at a certain depth, but since in this case the sluice gate doesn't go all the way into the normal depth, let's just leave a question mark here, and we'll see if that is a point of known water depth. And on the downstream end, where the water meets the lower reservoir, we know the water depth is going to be at that point. So let's mark that as another control point. So another important thing is for steep channels, the disturbances in water travel downstream because of the Froude number being larger than 1. Our adjustment to water level is going to be downstream from that point. For mild channel, the disturbances do travel upstream, so our water surface adjustment is going to be upstream from the downstream location or the downstream control point. So let me just start with the steep portion of the channel. So water starts at critical depth, but in any flow given time, the water will want to get to the normal depth. So here you start from normal depth at a pretty large angle, and it will approach the normal depth at an angle close to 0. So it's going to look something like this. So since the water is already at normal depth, it is not interacting with the sluice gate. In essence, the sluice gate doesn't affect the flow. So, and this will continue downstream along the steep portion of the channel, and we'll just leave it where the breaking slope occurs. For the mild portion, we start from the control point, and we know the disturbance travels upstream, so we begin drawing our curve upstream, and we stop at the breaking point, a point of breaking slope. So for the steep portion, the curve, let's go back to our nomenclature. So region 1 is above both normal and critical. Region 2 is between normal and critical, and in region 3 is the lowest, which represents a depth less than both critical and normal depth. So this one, since it's steep channel and it falls in region 2, it's going to be S2. Now this one, it was already at normal depth. There isn't a curve we need to worry about there. Now where the breaking slope occurs, there is going to be a hydraulic jump. And hydraulic jump is a mechanism that allows water to go from supercritical to subcritical regime. And since we don't know the exact force momentum in this condition, we will just point out both the cases and both the locations where hydraulic jump can occur. So one situation that could occur is the hydraulic jump could occur on the mild portion of the channel. So it will look something like this and approaches the critical depth line at a large angle. So mathematically it will be about 90 degrees. So critical depth line, and this one here is your normal depth line. So this is one possibility for hydraulic jump. This curve occurs in section 3. So it's 1, 2, 3, and it's in the mild section, so it's going to be M3 curve. The other possible location of hydraulic jump is within the steep portion of the channel, and the curve is going to take a large angle as it approaches the critical depth line. And this one, it's in the steep portion and falls in region 1, so that is our S1 curve. So these are two locations where hydraulic jump can occur. So these are possible locations. Okay, so now conceptually we know what the water surface will look like. There is going to be a hydraulic jump. We pointed out both the possible location for hydraulic jump. So either water is going to follow this track, goes up in a hydraulic jump and continues its way down this way till it meets the lower reservoir, or it will continue the route of the second hydraulic jump and end up in the second reservoir. Similarly, let's take a look at another problem here. So in this case, we have both mild channels, looks like. So this is your normal depth, that's your critical depth, and that's critical depth line and normal depth line. Make sure you label those on both sides. So here, that's a normal depth line for the downstream section. The critical depth line is the same. So first step, we find out the control points. On the downstream portion, where the channel meets the reservoir, we know the water depth. So this is our control point here. And this is mild channel here. And this one here is milder. So for mild channels, the disturbances travel upstream, so we'll start from the control point and work our way upstream. So as the water level goes upstream, it meets the normal depth line at a very small angle, looks something like that, and will continue on the normal depth line until something forces it to change the water depth. The curve here falls in region 1 in a mild channel, so that's your M1 curve. and once it gets to the break-in slope location, it is still a mild channel, so the disturbance or the adjustment to the water slope, water depth will happen upstream. So it will approach the normal depth again at a small angle. Once it gets to the normal depth, it will continue at the normal depth until something else forces it to change the depth. So here again, this one is in region 1 of a mild channel, so that's the M1 curve. So conceptually, we know what the water surface profile will look across the break in slope. Lastly, let's take at a third problem here. So here you have upper reservoir leading water into a steep channel, and at this point downstream the channel slope gets mild, so you have a mild channel following the steep channel, and then it ends up at a lower reservoir. Within the steep portion of the channel there's a sluice gate. The sluice gate goes through the normal depth line, so at this point we know it affects the water flow, so it is going to be a control point. So let's identify all the control points here. So the point at the inlet is our first control point. The point at the tip of the sluice gate is also a control point. We know the sluice gate will force the water to get to that level. And finally, where the mild channel meets the second reservoir, we know the water depth there, so that's your control point. Let's mark the channels here. So this is your steep channel, and the downstream portion is mild. We can begin at either end, so we'll just start from the downstream mild channel. So from the control point, the water depth is already at normal depth, so there's no curve here, and water will continue to be at normal depth unless it meets a forcing agent that will cause it to change depth. So we'll stop with the channel slope change occurs, and then we go to the upstream reservoir. So starting from the control point upstream at the inlet, water will approach the normal depth line at a small angle. It looks something like that. But since there is sluice gate, it will cause the water to back up. So the water here may back up, let's say, to a certain height, and it will approach the control point at a large angle. And let's mark the curve. So this one here, region 1, 2, 3. So this here is S2, and the curve up here is S3. 1. And since here the water goes from supercritical to subcritical, there is going to be a hydraulic jump here. So go ahead, mark your location for your hydraulic jump. On the location where the sluice gate is, the water is forced to the control point, and the water will then get to the normal depth at a small angle. It will look something like this. And this is going to be your S3 curve. Now, just like the first case, there are two possible locations where hydraulic jump can occur. It could either occur on the steep portion of the break-in slope, or it will occur in the mild section or milder part of the break-in slope. So let's identify both of those. You can either get this case again while the curve approaches the critical depth line. Let me just label those critical depth line, and that's your normal depth line here. Oh, here is that. So we already have critical depth line, so this one here is normal depth line. And this is also a normal depth line. Okay. So this is location of your first possible location of your hydraulic jump. This curve down here is M3 because it falls in region 3. So 1, 2, 3. The other location for hydraulic jump can be in the steeper portion. It will approach the critical depth line at a large angle, and that will be location of the next hydraulic jump. So this curve here is S1 as it falls in region 3 of the steep channel, and this one here is your location of possible location of your hydraulic jump. So that is it for today. Let me know if you have any questions, and I'll meet you during our regular recitation period. Thank you.